get started. We are still discussing the SNR, and we are still talking about how to calculate the SNR, pre-detection SNR and post-detection SNR, right? So let's review in the amplitude modulation case. So we learned the DSB, SSB, and amplitude DC added modulation, amplitude modulation, right? So in DSB case, we know that the transmit signal looks like this in equation, and also we know that the pre-detection SNR is measured right here, just after the antenna, after the bandpass filter, and before the demodulation. And post-detection SNR is measured all the way to the end of the receiver. So that is going to be after the demodulation, right? So in the pre-detection SNR here, that's before the demodulation. So always we want to remember that the noise power is going to be like this and not BT, right? Because this is an NT. This is a noise signal, power spectral density, right? So since this one shows you how the noise power is spread over frequency. This frequency you have this much of power in noise, right? So the total power of the noise is simply the area under this curve, right? Because this is a power spectral density. So simply that's going to be N naught BT, always for pre-detection SNR, okay? Pre-detection stage. So it doesn't matter DSB, SSB, FM modulation, AM modulation, anything, the pre-detection noise power is going to be like this. Signal power is a little bit different between the modulation because our ST is different, okay, for each modulation. So this is the case for DSB. So how to calculate the pre-detection is that you do a square because we need to calculate the power, and then take an expectation because we want to calculate average power, right? So this is the one, expectation of S square. That's always the case. And ST in DSB case is going to be AC MT cosine. So you would simply square. Then we know that AC is a constant, so that's going to be square. And M is your message. So M square and expectation, that's going to be our message, the power of the original message. Average power, your original message. So typically we can just put it as a P. Okay, all the time. Every time we just simply put this as a P. So again, the P is going to be constant. Okay, P is constant. So P, that's going to be constant. P, AC square is a constant. And cosine square expectation, we know that that's going to be 1 over 2. So simply in DSP case, it's going to be this one, right? And divided by noise power for pre-detection. So that's how to calculate the pre-detection. And also for envelope detection, like DC added modulation, we know that ST looks like this, right? And how to calculate the signal power is the same. Square of this and take expectation, okay? Then you're going to get this, AC square, bracket 1 plus K square P divided by 2. That's what you're going to get for signal power for DC added modulation. So you can simply calculate this. For SSB, same way. This is the signal. So you're going to square of this and take an expectation, same way. Okay? But in this case, when you do square of this whole thing and then take an expectation, when you square, since we have two terms, this square plus that square plus 2 times this, right? So we have a cross term. We have a cross product. That cross product will be 0 because we assume that MT and M hat T is going to be uncorrelated because, yeah, that's our assumption. So we do a cross product and take an expectation. Then eventually you're going to get expectation of MT times M hat T. So that's how to calculate the correlation. But we assume that these two are uncorrelated. So that term will be 0. So when you do square of this whole thing, what you end up getting is square of this term, square of that term. Okay, that's the only thing. But MT and hat T have the same power, right? Because this is a Hilbert transform. Hilbert transform does not change any amplitude. So the expectation of M square is going to be P. Same for this one. Okay? So eventually when you square and square takes expectation, these two will have the same value. So simply add it. That's going to be the power. That is the power of ACP divided by 2, I think, right? 4, actually, 4. Yeah, so that's going to be signal power. One thing that I want to tell you is this W, right? This is a filtered bandwidth. But earlier, when we talk about double sideband or DC added modulation, we always assume that the W is going to be BT over 2. Okay? Why is that? Because in DC added modulation and also DSB, what's happening is originally you have this in baseband. Now let's take a DSB. Let's say this is empty. Now you do a DSB modulation. Then we know that that's what the spectrum looks like. That's a ST. Okay? So we have a double side. But in single sideband case, if you take this one as a message in single sideband modulation, we know that it's going to be only half. Maybe this half or that half, right? Only half. So the bandwidth, filter bandwidth, is going to be, in this case for DSB, this is going to be W. But this one, this is going to be W. So now we have a different bandwidth for filter because our bandwidth of the signal is only half for single sideband. So simply speaking, for double sideband and DC added modulation, amplitude modulation, we typically assume that W equals to BT over 2. That's what you see here. But in single sideband case, we assume that this is almost same as a BT. Okay? For single sideband. So this is only true for double sideband or amplitude DC added amplitude modulation. But for single sideband case, we can assume that W is almost close, almost same as just BT. Okay? Because we are using only half of the bandwidth for single sideband. So that's how to calculate the pre-detection SNR. And post-detection, one thing that you want to remember is post-detection is measured after the demodulation. So after demodulation, we are going back to baseband. So here we are in the baseband, right? That's post-detection. So in order to go back to baseband, what happens is we get a signal here and go into the demodulation, but also the noise now come into the demodulation. So noise also go through all this demodulation process. So once you do that, noise is not like this anymore. This is a passband. Okay. Eventually, this noise also goes into the demodulation, right, and becomes a baseband. So noise will come in here again because we need to change it to baseband. So therefore, NT, the passband noise, NT, now we want to write it as this way. That's what we call as a baseband representation, right? So that's one thing you want to remember for post-detection. Okay? Post-detection is measured at the baseband. So NT needs to be changed to baseband representation like this. ST is the same as before. Okay? And the first thing happen at the demodulation is multiplying cosine. So multiply cosine here, multiply cosine here. Now all the other things is pretty much same as before. So you have a cosine 4 pi FC, sine 4 pi. These two will be removed by low pass filter, right? You only have this one. Okay, this one. That's going to be output of your demodulation. This one, right? So now at the output of the demodulation, we have message part or signal part. We have a noise part. So we are going to go do square of this and take expectation. That's the signal power. Expectation of this square, that's going to be noise power. So that's simply post-detection SNR. Right? So that's how to calculate. Same way for envelope detection. Again, you want to change NT, passband noise, into baseband representation and use ST for DC edit modulation and do the same way. Okay, pretty much. And single sideband, same way. Okay, single sideband, again the ST plus NT, but NT change it to baseband representation. Then NT has NIT cosine minus NQT sine. So we have ST also has two terms, and noises now have a NIT cosine minus NQT sine. So we have a two cosine term, two sine term, right? Okay, so we're going to do, we're going to consider that, and eventually in single sideband, we know that the receiver, we can use the coherent detector. Okay, coherent detector. So that's our demodulator. So inside the coherent detector, the first thing happen is you multiply cosine. And we have four terms, two cosine term, two sine term, and all of that we multiply cosine. So we have a cosine square, two of them, and cosine times sine, two of them. Okay, so clean that up by identity, using identity, we end up getting this. Okay, once we multiply that. And then this one goes into low pass filter. So this cosine 4 pi, sine 4 pi all goes away. Now we have only this one. So that's going to be output of your receiver, right? Coherent detector. So now again in the output we have a signal part, noise part. You can do the same way for SNR measurements. Okay, so that's the review. For FM, pretty much the same. In pre-detection, we know that this is a signal over the air. Okay, this is a FM signal we transmit over the air. So simply we do a square of that and expectation. In that case, this one is simply AC cosine, some cosine. So cosine square, the whole thing is going to be 1/2 anyway. So AC square divided by 2. That's your signal part, signal power, average signal power. And we know that in pre-detection, N naught BT is your noise power. So simply pre-detection SNR is this one. Okay, now we need to talk about how to calculate the post-detection SNR. Actually, this is the key. Okay, key of the this chapter, this particular subchapter. So here we are seeing the FM demodulation. Okay, in FM signal we have antenna here. Okay, we get this is a transmitted signal. Over the channel we added noise, right? And then that comes into the antenna. And first thing to happen is a band pass filter, because you want to receive only your bandwidth. All the other frequency you're going to reject. Now we get XT. So this XT is the same as always, like ST plus NT. So this is ST plus NT. Now we go through the limiter because we want to cut. Okay, we want to clip it, clip the amplitude. Amplitude doesn't matter for us. We just simply clip it. That goes into a discriminator. Mathematically, this discriminator is doing time derivative. This is the hardware, what hardware looks like. So discriminator, in graphical way, it looks like this. But this one, mathematically, is a time derivative. Okay. That signal goes into low pass filter, and eventually we're going to get the output. Okay. That output hopefully is same as original message. Okay. That's the demodulation. So now pre-detection was measured here, right? But post-detection, we're going to measure it here. So let's see how to calculate the post-detection. In FM, again, the amplitude doesn't matter, right? Amplitude doesn't matter. Okay, in amplitude modulation, right? Let's go back briefly here. In SSB, DSB, this kind of amplitude modulation, the noise, let's say you have ST plus noise, but the noise has some amplitude. So therefore, your original ST is amplitude modulation. Your information is in the amplitude, right? Because this is amplitude modulation. Your information is in the amplitude. But because of the noise, your amplitude will be changed because your amplitude plus some noise, and noise will change your amplitude. Okay? So that's why signal is now corrupted, right? So what is important here is amplitude part, because this is an amplitude modulation. Okay? What's going to be the amplitude added by noise? That's our concern here. Now, in FM signal, we don't care about the noise amplitude. Let's say, still we are looking at here ST plus NT. So this is ST plus NT, that's XT. So again, same way, noise has amplitude, some amplitude. So you transmit, let's say 1, but noise is, let's say, some 0.5, then eventually you're going to get 1.5. Okay? Because of the noise, your amplitude now changes, but we don't care. Why? Because we're going to cut it anyway. We're going to just cut. So amplitude change doesn't matter for us. Okay, then can we say that noise actually changes the amplitude, but we don't care? Then what does that mean? We ignore the noise amplitude, then is it going to be same as no noise? Because the noise is added only in the amplitude, and we don't care about the amplitude, then does it matter? Okay. That's why we want to look at this NT, okay, noise. So earlier in the amplitude modulation, we always think that this is noise gives you noise added some amplitude. But in fact, this NT, the noise, is a complex value, like A plus JB. So when you look at the complex value, any complex value, this is A plus JB. And we can also write this one as a phasor notation, right? Some amplitude with a phase, right? Any complex value, you can write it as a phasor notation. We know that, right? And earlier in the amplitude modulation, what we care was the amplitude part. Phase doesn't matter, because in the amplitude modulation, your information is in the amplitude. So for the noise, also we are looking at only amplitude. However, in FM modulation, we don't look at amplitude. Okay? Your message is inside the phase, not in the amplitude. Your message is part of your phase. So now our interest, what we are looking at is, when we look at the noise in FM, we're going to look at phase. Amplitude, we don't care. We're going to look at only the phase aspect of your noise. Okay, that is important. Phase is important for us, for noise. Okay, so that's the difference between the amplitude modulation and FM. Okay, because your message is in the phase. When we look at the noise, we are also going to look at only the phase in the noise. Okay? Not amplitude. So let's continue here. So we're going to start from here, xt. Okay, xt. So xt, we know that it's going to be st plus nt, like that. Okay, and then st, we know that it's going to be ac cosine Let's write it this way. We know that this phase is T we know that in frequency modulation, actually this phase change should be a integration of your message, right? This is FM signal. That is ST. Now for the N plus NT, but for NT, okay, for NT, we're going to write it as this way. So that is RT cosine 2 pi FCT plus phi n t. So this is going to be our nt. Okay, that's our nt. Why do we write nt like this? In the amplitude modulation, when we discuss the AM, DSB, SSB, we never write the nt this way, right? We simply write nt as just nt. That's it. Because at that time, we were only interested in amplitude. But as I said, nt is actually a complex value like this. So therefore, it has an amplitude, but it also has a phase. And in FM, we are interested in the phase in the noise. So therefore, we're going to write this way. RT is amplitude of the noise. And cosine something and phi nt, this is going to be the phase of the noise. Okay, so we're going to look at the important thing in FM is this one, phi nt. This is a phase of the noise. Noise has its own phase. And this one is going to be the phase of this one, right? Signal part. But this is a phase of the noise. So that's how to start. Okay, for FM. Now once you look at this, right? We know that this is a vector and this is another vector. We are basically adding two different vectors. Okay, each vector has an amplitude. This vector has amplitude AC and phase this one, phi1, phi t. This is second vector. The size, the length of the vector is RT, and phi nt is another vector. So let's draw this vector addition. So let's say this is a vector for the ST. Just assume that. Then this length is going to be AC. Right? Okay, I'm basically drawing this first vector. And this vector has a phase of phi t. So this angle here is phi t. That's our first vector. That's our first vector. Now let's look at the second vector. Okay, second vector has amplitude RT with a phase R and T. Okay, so let's draw that in origin here. So let's say second vector like this. Just assumption, okay? And this second vector has the length of RT. This is RT. And this angle here is phi nt. Okay? So we are basically drawing two different vectors. So this is one vector. This is a second vector. Okay, so in this picture, you can see that this black one right here is a vector for the first term. And this red one here, okay, that's going to be the vector for the second part, which is the noise. Okay, so we are basically drawing two different vectors. First one, second one. This is ST, that's NT, basically. Now what's happening is XT is ST plus NT. So we are adding these two vectors. So when you add these two vectors, how to do that is move this second vector into the end of first vector like this. Okay, shift that here, right? That's how to add, right? So eventually the output, when you add these two vectors, the output is going to be this point. Okay, so what is XT? XT is from here to this. That's XT, right? That's the addition of these two vectors, XT. Okay, so in this picture, you can see that this blue arrow. Okay, you see that this is resultant, right? This blue one. This blue one is XT. Addition of these two vectors, right? I'm basically simply adding the black vector with the red one. Simply add these two vectors. Output is going to be the blue one. Okay, that's what I'm drawing here. That's xt, right? We are interested in looking at xt. Okay, that's what we are looking at here in the vector notation. We want to look at a little bit more carefully about xt here, and what we are interested in. Eventually, what we want to find out is this angle. What we are interested in is the angle or phase. We don't care about AC or RT or this size. We don't care. Amplitude, we don't care. What we care is angle or phase. And eventually, what we are trying to find out is this angle. That's what we are trying to find. Okay, what is this? Okay, that's what we want to get. That's our goal. Okay, we want to find out that goal. So how do you calculate this? The angle between these two vectors. Angle between ST and XT. How do you calculate? So how to do that is, first of all, we want to extend this ST and make a right angle like this. Okay, right angle. Now then, we know that this length is RT, because we just simply move this vector here, right? And what is this angle right here? That angle actually is same as this one minus this. That angle is same as this angle. Okay, right? This angle is same as this much, because simply we shifted, move this one here. This is same as this, right? So simply this angle is same as this. So that is gonna be this minus this, right? And this whole thing, we know that it's a phi n t minus this angle is phi t. So that's our angle here. Okay, let's call that one as this one, this one, psi. So let's call it as psi t. That's this angle. Okay, once we know that, we can see that this size is RT, this angle is psi t. So this, from here to here, okay, from here to here, we know that this is going to be RT, which is this size, times cosine psi t. This one right here. And this length is going to be RT times sine psi t, right? So here that's a RT times sine psi t. This is RT times cosine psi t, right? We know that. Right? You know that? So now we can find out this angle. Eventually we want to find out this angle, right? This angle. And now we are, you can easily calculate that because we know the length of this. We also know the length of this. Now we want to consider this triangle. This triangle. Okay? This is here we have a 90 degree. So that is going to be like this, right? Like that. So we know that this size is RT sine psi t, and this one is the size of xt, which is AC, and this one actually is, oh, no, this is not AC, right? Okay, no, this is not AC actually. Yeah, this is not AC. This is AC. From here to here, this is AC. from here to here, right? That's the size of your original ST. So this is AC. Plus we need to add this one, RT cosine. So here, this amount is RT cosine phi t, psi t. So now we know that this is this plus this, and this one is this. And we want to find out this one. And we know that this triangle has a 90 degree here. So we can simply calculate this, right? This angle, we can call this angle as theta. Okay? Then theta t, actually tangent theta t is going to be this and this, right? So that's going to be RT sine psi t divided by AC plus RT cosine. Right? So that's a theta. This actually that's not theta. No, that's not. Okay, let me take it back. Wait, not theta. Let's call as this. Okay. So this I'm talking about this angle. This angle right here is gonna be okay, 1 second. Okay, since we need so many symbols, you know, this it says that phi r. We have phi and phi r, psi. We have so many of terms, but what I'm talking about is I'm trying to get this angle right here. So this angle in here we call this a phi r. Okay, this phi r is this one. Okay, that is this angle. So how to get the phi r is the tangent inverse of this. Okay, then we're going to get this phi r. So eventually this phi r t is tangent inverse of this one, like this. Okay, so that's that angle. You see here, right? So this is a phi r t. That's what we want to find out. Okay, that's what we want to find out. And once we know this angle right here as a tangent inverse, now this tangent inverse angle, this phi r t, plus this one is a original phi t. This angle is the angle phase for the original ST, right? So phi t, which is this, plus the additional angle here, this tangent inverse, that's going to be the whole theta t. Theta t is the angle of xt. Okay, angle of xt. So eventually, what we are trying to do is we are looking at xt, right? And we want to find out what is the phase of xt. That's what we are trying to get. What is the phase of xt? We know that phase of st is this, and phase of noise is this one. But what is the phase of this xt? That's what we want to get. Okay? Because in FM, what is important is phase term. So we want to find out the phase of xt. And this is how to calculate the phase of xt. And eventually, the answer is this one. So this is going to be the phase of xt. Theta t is the phase of xt. You know, it's not like phase of xt is pt plus pnt. That's not like this, right? Okay? We have two vectors, and you cannot simply add these two phases. That's not the answer, right? And you need to do this way. You need to draw the vector diagram like this, and then calculate the phase of your xt. So this is a phase of xt. Okay, xt has amplitude, but we don't care. What is the phase of xt? This one. Okay, that's our starting point. So we know the phase of your xt like this. Now in here, we know that AC, look at here, AC is pretty large, right? AC is pretty big, and much bigger than this part. Why is that? Because this RT is a noise amplitude, and cosine, still this is a part of your noise. This is your signal. And typically, AC, which is this big arrow, AC is much bigger than this noise amplitude, typically. Why? Because if the noise amplitude is even bigger than signal, then you're not going to receive anyway. You cannot detect the signal anyway, right? Generally in communication, your signal power or signal amplitude should be larger than noise, right? That's the general case. So AC is typically much larger than the noise part. So we can simply, in here, you can ignore this because this is much larger. So ignore this. And also, we know that this is a tangent inverse, right? Arctangent. So what does the arctangent function look like? Arctangent function looks like this, right? We have a phi over 2 here, minus phi over 2 here. So this one look like this. That's the what arctangent function look like. So if the tangent inverse x, okay, this is x. If the x here is a small value, like somewhere here, then we can approximate arctangent x as same as simply x, like this, right? We can simply use this approximation. When the x is small value, okay, when x is small, then we can typically we approximate this way. Arctangent x is just x. Okay, we can do the similar thing for sine, right? Sine x simply approximated as x when x is small. Same for tangent, arctangent. So therefore, the arctangent, okay, arctangent inverse x, and this x is pretty small, right? Why? Because this what is this one? This one is this angle right here. Okay, this right here is this angle, and this angle is actually pretty small. Why? Because the noise has small amplitude. Think about this. Noise, this red one, red arrow, this is noise amplitude, right? Noise amplitude is very small. So since this is small, maybe you can change it. Still, this angle is very small, right? Because noise size is very small. So this angle right here is typically pretty small. So this one is a small value. Therefore, tangent inverse x, we can simply simplify it as x. Okay, and also AC plus this, AC is much larger than this, so we can simply drop this one. So eventually, when you do all that, then we're gonna get this. So we drop the tangent inverse, okay, because of this approximation. There's no tangent inverse, and also on the bottom here, we had AC plus R cosine, okay, but R cosine we drop it because AC is much bigger than RT cosine. So we can simplify the phase of your xt this way. So this one is the phase of the noise, phase of xt. Okay, phase of the xt. Using a little bit of approximation of this. Okay, we use a little bit of approximation, but still, this theta t is the phase of your xt. Okay. Now, in phase of xt here, eventually what we are trying to still okay. So let's look at here. We look at the 3 theta t, but we are still here. We are still here. What we are trying to do is we want to look at what this xt looks like. Okay, we haven't gone to yet. Okay, we haven't gone further yet. We are still here. We are still here and trying to look at the xt in a different aspect. We are looking at the xt from the phase aspect. So that's this one, theta t. Okay? So now it's time to go in. Now it's time to go into the discriminator. And what is the discriminator? its time derivative. Okay, so that's the next thing to do. So we know that xt has this phase, and eventually we want to take the time derivative like this. Okay, that's what happened inside the discriminator. Okay? That's what happened inside discriminator. You know the vt, that's the message, is 1/2 and time derivative of theta t. When we discussed FM, we already looked at this one. Okay, just to look at your previous lecture note in FM. So we already learned this equation. So this is the mathematical equation for discriminator. Okay, just simply take a derivative of your phase. So why? Okay, let me review. So earlier, when we talk about FM, we didn't consider noise, right? We only looked at a signal, and there was no noise at that time. Right? So that was your ST. But the phi t, which is the phase term, is this one. That is our relationship in FM signal. And our eventual goal is to bring this out, right? Message. We want to recover the message. So how do you recover the message in FM? First thing to do is we need to know the phase, because the message is part of your phase. So we need to know what the phase looks like. And then what do you need to do? You need to take a derivative of the phase. That's how you recover the message. Right? Because once you do that, now we're going to take a derivative of this one. Then let's take a derivative of this. When you do that, then you're going to get 2 pi kf and mt. So 2 pi cancel out. You're going to get this one. Okay? So that's how you recover the message, right? So that's FM, simply. This is the signal over the air in the FM case. Find out the phase of the signal over the air. Okay, so we have an FM signal over there. So grab the signal and look at the phase and take a derivative. Just put it into the time derivative. You're going to get the message. So that's FM, right? We're going to do the same thing, but the only difference is now we're going to grab the signal over the air. That's not this one. Instead, when you grab the signal over there, what we are getting is xt. That is the signal you are going to get over the air, right? Because we have noise. So now we also have a noise, right? But still you are going to the same process. Same process. So in the earlier, okay, when we have only signal, what we did was get the phase and take a derivative. That's what we did. Let's do the same thing, right? And when you grab the signal over there, what you're getting is xt. Okay, so get the phase of xt and take a derivative. Same way. So what was the phase of xt? That's this one. This is when you grab the signal over there, look at the phase. This is the phase. Okay, that's the phase. Now what we need to do is put this phase into the time derivative. That's what happened here. That's what we are trying to do here, right? So let's take a derivative of this one. Okay, then we're going to get the signal. Okay. Once you do that, let's take a time derivative of this. So this is a phase of your xt, phase of your xt. Now what we want to do is we want to do time derivative like this. In that case, we're going to take a time derivative of this one, simply, plus time derivative of this. Something like that, right? Something like that. Yeah, you're going to get something like that. This part is easy because this is signal part. Okay, we already did that before. So what is the d phi t? This is kfmt. I just did, right? I just did. So this is the kfmt. So we know this one simply goes into here. This is the recovered message, okay, from the FM. So if there is no noise, then we're going to get this one, okay, once you take the time derivative. However, now what happened is we have a noise term, which is this. That makes it complex. But let's look at the simple way. In order to look at the simple way, what we want to do is that we can simply introduce a simple symbol here. Let's substitute RT sine psi into NQT. Okay, so let's put it this way simply. Okay, NQT. So RT sine psi t is the same as NQ. Just make it NQ. Then here, when you put this one into time derivative, you know that this is the time derivative of NQT. Okay, that's what we're gonna get, NQT. So in this equation, okay, in this equation, we know that the time derivative of Vt, that's gonna be kfmt. We know this part. We don't know yet is this one. This is the only thing we don't know yet. We know this one already, but we don't know this. So this is our concern right now. We want to find out what this looks like. Okay, some of the noise NQT and time derivative of noise. Okay, that's what we want to find out. So this is what we are going to look at from now on. Okay, so here we right here in the last equation, this one d dt nqt, this one even replaces ndt. That's what we have here. So d means derivative. So noise derivative equals to this. Okay, that's what we have here. So eventually what we want to find out is ndt. Okay, ndt. That's what we want to see, this ndt. Okay, so let's take a look at the ndt, what it looks like. Okay, but let's go back a little bit. I'll tell you what that means. Right now what we are doing is we are taking time derivative like this, right? We're taking time derivative. So in block diagram, we are actually going through the discriminator. This is a time derivative, right? That's time derivative. This is a mathematical equation. And in the actual system, right now we are doing this one. That is a time derivative. And what does this discriminator look like? Like this. That's a time, that's the discriminator. Okay? This is discriminator. Right? So what that means is your signal, we have xt. Xt has a signal also noise. Signal part goes into here, and then you're gonna get output of this. And now the noise part also goes into time derivative, or noise also goes into here, and then you're gonna get the output. That's gonna be like this. That's like this, right? So we want to find out what this looks like. You know that the time derivative of some function, when you look at this in frequency, it's actually equal to multiplying j2 pi f into, okay, so if you have, let's say, xt, and frequency response of this xt is xf. So this is a time domain, this is a frequency domain. Okay, some function, some signal. Now you want to take a derivative of in time. That's going to be same as you multiply j2 pi f in frequency, right? So that's some simple relationship between time and frequency. And what's happening inside here is the time derivative. Okay, so when you look at the same thing for in frequency domain, we are simply multiplying j2 pi f into the frequency response of the signal. So that's basically the same thing. So we're going to look at in frequency domain here. Okay, so this is what we want to find out, ndt. Okay, that's what we want to investigate a little bit more carefully. Okay, but that is actually the time derivative of dq, nq, right? That's what we want to look at. But since this one is a time derivative, we want to look at this one in frequency domain. Okay, simply when you look at this one in frequency domain, when you look at this simply frequency domain, then we know that this time derivative is equals to multiplying j2 pi f, and we already have a 1 over 2 right here, and 1 over 2 AC as a constant value right here. This is a constant value, right? And this time derivative is same as a j2 pi f in frequency domain. So change these things in frequency domain, then it's going to be like this, right? 1 over 2 pi AC still there. And this time derivative is same as multiplying j2 pi f. So that's here. So we have a 2 pi cancel out. Okay, so this one basically will be changed to this one, jf divided by AC. Okay. Okay, simply what I'm trying to say is this is what we are trying to do in time domain, but we want to look at this in frequency domain. This constant value still there, and this time derivative is going to be same as multiply j2 pi f. Okay. Of course, we have nt, and that's going to be changed into nq sum f, right? Of course. So that's what's happening. This is simply time domain. We are doing the same thing in frequency domain. Now we have a 2 pi, some constant cancel out like this, right? And then what is remaining is AC times J, F, and some noise frequency response. Okay, so that's what we are doing. Now, what we want to look at is that what is this NQF? This one, and also this NT, right? This one is a noise signal over time. And this is a noise response in frequency. Okay, so this one NQT tells you the noise amplitude and each instantaneous noise value. NQF is the frequency response, and we are not interested in noise frequency response. instead what we're interested in is noise power spectral density. This is not power. So we always want to look at the power spectral density. Remember that earlier in AM case, we also looked at only power spectral density, right? Yeah, we want to look at the power spectral density. So in order to get the power spectral density, we need to do square of this, right? That's how to calculate the power spectral density. So when you do square of this, okay, in order to get the power spectral density, let's do square. Okay? When you do square, you take some abstract value square, okay, and then you're gonna get this one, f squared divided by ac squared, and some just square of these things, okay. Again, when you do power, the amplitude, this one hold the square, and NQF, this is just simply frequency response. So we are changing this one into the power spectral density. So when you look at the power spectral density, it's going to be f squared and ac squared and power spectral density of NQ. That's what we get as power spectral density of this noise. Power spectral density. Okay, that's important thing. Power spectral density, square of that. Now what we can see is this is the clear difference. Clearly difference between the FM and AM. Okay, remember what the power spectral density looked like in AM? Let's go all the way in AM, right? In DSP, SSB. We looked at the noise NT, and NT in passband has this power spectral density. This is a passband. But eventually when this noise go into the demodulation, and as output, you are going to get NIT, right? We always get the noise. This NT goes into the demodulation, right? When this NT goes into demodulation, and eventually you get the output, what does the output look like in noise? That's going to be always like NIT, right? Look at this NIT. This is part of your noise. Okay, this NIT is the output of here, output of the demodulation. When you get the noise here, and noise go through the demodulation, something will still survive, right? This is the noise output of the demodulation, NIT. And what is the power spectral density of this NIT? Simply like this. Simply the noise spectral density of NIT is like 0, like this, flat. And this top is N naught. Okay, we have this is a BT over 2. This is minus BT over 2. So this is a power spectral density of NIT. Actually, this one, we can say S NIF. That looks like this, right? So in AM, the power spectral density of your noise at the output of the demodulation looks like this, flat. But in FM, we have this one. So let's look at what this looks like. You know, this one has F square, right? F square. So let's go to this one square. So this is our power spectral density of your noise when we use FM. So what does this look like? This one looks like this. Okay? Because we have F square, right? You know the X square looks like this, quadratic function. So this is a clear difference. You know this one, somehow this one is a noise power spectral density when you use AM. Amplitude modulation, you still have this noise power spectral density. But in FM, instead, you are using, you have this noise power spectral density. We have F square, right? F square. So what does it tell you? In AM and FM, noise power spectral density is very different. So what does it tell you? What this means is which one has a, okay, so This is a noise. This is power spectral density. So how do you get the power? Simply calculate the area. That's going to be the power, right? Because this is power spectral density. Which one has a large power? This one has a large power. Or another way, this one has smaller power, right? In FM, noise has much smaller power. Eventually, when you go all the way through the demodulation, this is the output of the demodulation. You already passed all of the demodulation, FM demodulation, and you go all the way to the end. Okay, recover the signal. You're gonna also go through all the steps of demodulation. Eventually, you're gonna get this noise power spectral density, and you know that noise power is much smaller in FM compared to AM case. What does it mean? This is why FM is much better, right? In AM, noise power still has this much, right? But in FM, when you use FM signal, FM modulation, and FM demodulation, your noise power is much reduced by this. Your signal is recovered, no problem, and noise is reduced by this much. So that's very big difference, and this is why the FM is typically much higher SNR. Signal power is the noise power is smaller, so in SNR, when you have a smaller noise power, SNR is high, right? Because noise power is on the bottom. Okay, in the denominator. So this is a noise power, and that makes a clear difference. So that's the message in FM. And this is the equation for power spectral density, noise power spectral density. So in equation, you see that you have a F square divided by A square, right? This is the mathematics. This is an equation. When you draw this one in picture, this is what picture looks like. This is a graph. This is the equation. Okay? Yeah, so that's what it is. Now, we want to calculate the post-detection SNR, right? Eventually, we want to calculate the SNR, post-detection SNR. To do that, we need to calculate the noise power. So now we know that this is a noise power spectral density. How do you calculate the noise power? You calculate the area. This is like high school mathematics, right? You're doing integration of square. So let's go back here. This is the equation. Integration. When you do integration of f square, you're going to get like f. You do this, right? This one. Integration of f square. Of course, this n naught divided by ac squared. This is simply constant. So constant, you just move it to the front. And integration of f square. When you do that, it's going to be 1 over 3 f to the power 3, right? Simply. So you're going to get this one. This is your noise power. So noise power actually looks pretty different here, right? But this is a noise power for post-detection. Okay. What is the signal power? We also need to know the signal power. Only then you can get SNR. Signal power is simply this square expectation. Okay. So what is that? Kf square p. Okay? That's going to be your signal power. Because this is what we do eventually. We know that this is the signal part. This is a noise part. Signal part is easy. We get this one. So signal power is easy to get. But noise power is a little bit difficult to get. That's what we discussed here. Eventually, when you do this whole thing, we know that the noise power has this spectral density. And then you do integration of this figure here. Now you get this noise power. So this signal power divided by this noise power will give you post-detection SNR. Okay?